So, (3.2) state and output equations. Okay, this is the we're finally getting there, and I'm getting excited. You guys don't even know how much fun is in store for you right now. So much fun. Okay, the state x, input u, and output y vectors interact through two equations. So 3.1a and 3.1b are those two equations where f and g, so we have x in there, u in there, t in there, y in there. The only things that we haven't seen yet are f and g, and they are vector-valued functions that depend on the system. Okay. Together, these two equations comprise what is called the state space model for a system, or a state space model for a system. So we had a linear graph model that we learned how to construct in Chapter 2. In Chapter 3, we're learning how to construct state space models based on those linear graph models. Okay, and let's dig a little deeper in here. I say let's not glide past these equations because they would be our dear friends for the rest of our analytic lives. Okay, they're so cool. Okay, these equations describe a great number of dynamic systems that you could want to consider. So let's unpack them a little bit. The first equation here is called the state equation. Given state and input vectors at a moment of time, so state vector, input vector, at a moment of time, its function f here describes how the state is changing. In other words, what its time derivative is. What is the time derivative of the state? So the time derivative of the state, the slope of the state, the trajectory of the state, how the state is changing at a given moment in time, is determined by the state, the input, and what time it's at, what time it is. What time is it? State time. I don't know. Okay, so this is our sort of fundamental equation right here. So it's a vector equation. So we packed a lot into it. So we didn't have to write very many symbols down, but we got a lot of information packed in. Okay, it's nice. Okay, good. Clearly, the state equation, 3.1a, is a vector differential equation. So what I mean by that is it's a differential equation, time derivative right there, right? And it's a vector equation, meaning there's a vector on the left-hand side that equals a vector on the right-hand side, right? Which is equivalent to having a system of first-order scalar differential equations. Okay, so if I wanted to, I don't really want to, but I'm going to give it a little peek. We could write the left-hand side. So if you take the time derivative of a vector, or the derivative of a vector, what you do is you take the derivative of each of its components. Okay, so dx dt is just, I'm going to use dot notation, x1 dot of t, x2 dot of t, down to, there are n of them, right? xn dot of t. That's the left-hand side. The right-hand side is f1. So f is a vector valued function. So f1 of x, u, and t. f2 of x, u, and t down to fn of x, u, and t. See, the compact notation was so much better. Right? But what we're saying is this component of the left-hand side is equal to this component of the right-hand side. And if that's true, then we have a system of coupled, probably coupled, in general coupled, first-order differential equations. The time derivative is only order 1, right? So first time derivative. So that is the state equation, and it's everything. Okay, it's everything. All right. So in accordance with the definition of a state-determined system from lecture 3.1, the one we just finished, given an initial condition, so the state vector at an initial time, and the input, the state x is determined for all time greater than or equal to the initial time. The state space model is precisely the mathematical model described in the definition of a state-determined system. Okay, so remember from the previous lecture over here when we were all, oh look, state-determined system, if we know these three things, then we can determine what the state is for all time. Well, actually, I did say mathematical description. I could have substituted in there model, and this would have come out a little bit smoother, but you guys get the idea. So, at least I think you do. We're going to pretend like you do. Okay. I'm sure you do. So, I told you guys that it was going to be differential equations. The state equation is that set of differential equations that describes the system. Okay, so the state space model, so determining the state requires the solution, analytic or numeric, of the vector valued differential equation. Okay, so you got to solve the state equation, also called the equation of state, just to sound cooler. So the second equation, so we mostly have just described this first equation so far, right? State equation, bam. This one is like everything, and then this is like whatever is left over, which is very, very little. Okay, so the second equation is algebraic. Notice there are no time derivatives in this. So it's algebraic, it's not differential. It expresses how the output y can be constructed from the state x and the input u. This means we must first solve the state equation to get x, right? So we solve the state equation, we get x. We already know u. We want to know this solution for all functions, for all values of time. If we know x, then we know g is just from the system, so we just get y from that. So how this works is step 1, define the output variables. So what am I interested in from the system? Back on the in the previous lecture, we said, oh, okay, like maybe we care about what one of the state variables is, or maybe we care about what the current through a given resistor, IR7, we said the current through resistor 7 is what we care about. So we determine what that is, and that's the first step, and then we write each of these output variables in terms of state variables and input variables. Okay? So I'll flip back to the other lecture quickly. We said, oh, okay, IR7 is an output that we want. Great. That was step 1. Step 2 is to write IR7 in terms of state variables and input variables. So you got to write IR7 in terms of like IL1 and IL2 and VC1 and VC2. Maybe you only need so maybe R7 and L1 are in series, so they have the same current. So maybe IR7 is just equal to IL1. That would be convenient, right? It's an easy way to write it as a state variable. It could also depend on the inputs directly as well. Okay, good. So just because we know that for a state-determined system, the solution to equation 3.1a, that is the state equation, can be determined, doesn't mean we know how to find it, right? So just because we know it's a state-determined system and this is its state space model, doesn't mean we know how to solve that differential equation. In general, f and g, so f and g more explicitly, take in something from Rn, which is to say they take in an n vector, which is the state vector. Take in a state vector, they take in an input vector, and a value of time, and they return something that is in the state vector space. Actually, it's the time derivative. G takes in something, it takes in a state, takes in an input, takes in a time, and it returns an output vector in Rm. So f and g in general can be nonlinear functions. So not the best. If f and g are nonlinear, especially if f is nonlinear, it's not great. We don't know how to solve most nonlinear state equations analytically. But don't fear. That doesn't mean we're done with our test. Okay. So an additional complication, in addition to having nonlinearity that can happen, an additional complication is that in addition to the states and the inputs being time varying, system parameters can themselves be time varying. So back up here, we said f could be a function of x, u, and t. And if it's actually explicitly a function of time, that means that something like the mass is changing as a function of time, or like the resistance is changing as a function of time. That is a little bit easier to deal with than nonlinearity, actually, but it's still not fun. But fortunately, so fortunately, a linear, and I was supposed to insert here time, invariant model, actually not there, right? We have an errata on the errata. So the linear time invariant model is sufficiently effective, and then there wasn't supposed to be a period there, it was supposed to be most of the time. Well, I will say often, because lazy. Okay. All right. Now, we have ourselves our state equation, our output equation, but in general, f and g in this form can be nonlinear or time varying, and we're saying, well, usually we can get away with a linear model, some operating regime, and we'll talk about that idea another time. But a linear time invariant model has a really specific form for f and g, okay? And we're going to write that now. So a linear time invariant system has the state space model that the time derivative of x, so left-hand side is the same, it's equal to some matrix times x plus some other matrix times u, which is to say the states enter in such a way that you can write a matrix A to describe how it enters in, and the inputs enter in such a way that you can write a matrix B that describes how the inputs affect the change of the state. Okay? Also, the output can be written in this way, Cx plus du. So the state and output equations can be written in matrix form because they're linear. Okay? So linear algebra is about algebra that can be described, or algebra that describes linear systems. And that's why we can write a linear state equation and a linear output equation in this form with matrix vector multiplication. It's because we have this ability to write any linear set of equations in terms of a matrix multiplying a vector in that form. So you guys probably saw this when you learned how to find the product of a matrix and a vector in the pre-calc classes. I think a lot of people do that, or maybe in calculus, to Calc 3, or Calc 4, I guess is called the community colleges around here, slash vector calc. So, taking a matrix, multiplying a vector. You guys probably learned this at some point in some class for describing a system of algebraic equations. And then you would solve it using so-called Gaussian elimination, and maybe taking like a matrix inverse, finding the inverse of a matrix. These are things that sound familiar and you don't totally remember probably. They're a little foggy. For those of you who haven't taken linear algebra, don't freak out. I'm not going to require that much of you in terms of matrix and vectors in this semester. Next semester I'll require a lot more. Currently, this is like the whole of it. You got to be able to understand these equations. How to construct a set of equations in terms of a matrix times a vector. And you guys have all done matrix vector multiplication, I hope. Okay, so we have 3.2a and 3.2b, our linear state and output equation, so our linear state model. So A is, and we're going to do the dimension of the matrix, and we're going to say how the matrix is affecting the equation that it's in. Okay. So A is an n by n matrix. So it's not symmetric. It's square matrix, n by n, that describes how the state the state's coming in and A is multiplying that state, right? So it describes how the state changes so the state equation is all about changes to the state, right? So it describes how the state changes the state. I know. Okay. So what this means is, well, if we think about the state changing the state, where you are in state space, or what your current state is, affects how you're going to change, how the state's going to change. Okay? So for instance, if you're in a state, if your system is in a state that has a spring that's stretched, that's going to affect what's going to happen next, right? If your current state is that you've stretched the spring way out, the next state is going to be affected by this fact, right? That's the kind of thing that the A matrix will be governing. We'll be saying, oh, if you've stretched a spring a long way, you're going to be moving in this direction, okay? Changing the state in this direction. All right. B is an n by r matrix that describes how so the B is multiplying the input, right? So input comes in, B operates on it. So it describes how the input changes the state. Again, right? It's in the state equation. So it changes the state. So A is describing how the state changes the state. B is describing how the input changes the state. C is an M by N matrix that describes how so what do you guys think? Help me out with this one. So C operates on the state vector, right? And it gives you a contribution to the output. So C is an M by N matrix that describes how the what contributes.
State.
So how the state contributes. Great. How the state contributes to what?
Output.
The output. Great. And it's an additive contribution, right? D is, and let's try to figure out, this was the hardest one dimension-wise for people usually. So let's figure out what the dimensions of the D matrix are. Okay? Everybody remembers that if you have I shouldn't use A and B. If you have an alpha by beta matrix multiplying a gamma by delta matrix, delta. What is the dimension of the matrix that comes out?
A by delta.
So it's alpha delta. Alpha delta. But and the requirement is these have to be equal, right? These must be equal. And what happens is the inner dimensions collapse and you get the outer dimensions, right? And it's always row column, right? Row by column. All right, so if we need to get out something that has the dimensions of the y vector, that means that, so the y vector is an m by 1, right? An m vector. And you have to multiply u, right? So we know first off that D has to have the first dimension be m. Because whatever it's going to multiply on its right-hand side, it's not going to collapse that first dimension. So it's got to come out to be m. So the left dimension's got to be m. So I'm going to write is an m by, what is the dimension of u?
R.
R. An m by r. So what we have is an m by 1 multiplying an no, not an m by 1. An m by r multiplying an r by 1. Right? R by 1. So u is the vector, r is r by 1, m is the matrix, m by r. The inner dimensions collapse, and you get an m by 1 out, which is the correct dimension for y. So that means our D matrix is an m by r matrix that describes how the what contributes to the what.
The input contributes to the output.
Yeah, exactly. Input contributes to the output. In the next 2 lectures, which I don't think I'm going to have time to do this weekend because it's a long weekend, but I would like to do. Give you guys bonus lectures over the St. Martin's Day weekend. Isn't it St. Martin's Day Friday?
Yeah.
Okay.
Veterans Day.
Also Veterans Day Friday, so it's a big day. So in the next 2 lectures, we will learn how to derive the linear state space model So 3.2 from its linear graph. Okay. So this is important. I want you guys to come back for me just for a second. I know it's late. You guys want to do lunch, but we're going to derive 3.2 from the linear graph models that we've been learning how to derive already. Okay. So this is the link in the next 2 lectures between linear graphs and state space models. All right. Have a good weekend.